This is the solution to problem 428 of Halliday, Resnick, and Walker. So let's go look at the problem. We've got a projectile, a stone in this case, is given an initial velocity up, travels upward in this arc, and comes down, hits the top of the building, or the cliff, I guess, actually. And we know the initial speed, and we know the initial angle. And then we're asked various questions about, we also know how long it takes for the stone to get up there to the top of the cliff. And then we're asked various questions: what's the height of the cliff, the speed of the stone, etc. So as usual, excuse me, I like to sort of ignore those questions first, and let's just talk about the motion a little bit. So the first thing I always want to do is set up a coordinate system, and here it seems pretty reasonable to make the origin of the coordinate system down here where the stone is first projected. And let's choose the positive direction as upwards plus y. That seems to make as much sense as any, so we'll go ahead and work with that as the sort of standard approach. So then, having done that, we can say, all right, well, what do we know? We know this initial velocity, v0, and we know its angle, theta is 60 degrees, so it seems like we're going to absolutely need to have the horizontal and vertical components of that, so let's go ahead and do that. The x component is, of course, x component, always good to draw these vectors, and y component going up. So the x component is the adjacent side, that's going to be the cosine of theta, which you put in the numbers, the initial velocity and cosine of 60, and put that into your calculator. That comes out to be 21 meters per second. And then we could do the same thing to find v0y. That's clearly going to be the other. That's going to be sine of theta. That's this guy. And if you put in the numbers there, that comes out to be a larger number, as it should, according to the picture there, 36.4. Notice I explicitly included the plus sign. It's, of course, plus up here as well, but the vertical stuff can get a little confusing sometimes. But again, we've chosen our positive y direction to be upwards. All right, so having that initial velocity in the x and the y direction, now the question is, what are the equations that we have that describe this motion? And I think we're pretty clear that this is projectile motion. There's no acceleration going on in the x direction, and there is acceleration in the y direction. And notice I'm going to write that as the acceleration is negative a sub g, because I always consider a sub g to be a positive 9.8. So I'll explicitly use minus a sub g to represent that acceleration in the y direction. And it's minus in this case because we've chosen the positive direction upwards, as I've said a number of times now. All right, so what are the equations of motion? Well, if we think about the x direction, that's pretty straightforward. Just distance, x is equal to v times t is the equation there, because, and I'll write it down here, it's kind of obvious, the velocity as a function of time really isn't a function of time, it's just a constant v0x. For the y components, we know that the y is given by the constant acceleration equation, where now we have some acceleration in the vertical direction. And again, notice the minus sign I put out here because we're thinking of a sub g as a positive number. That's the position. We can also write the velocity as a function of time as well, and that's just the standard result for constant accelerations. All right, so I think we can go now and ask, or look at this first question. What's the height of the cliff? Now, we know how long it takes to go through this entire motion, but you can ask a question, do we need to sort of break this up into two pieces, namely the motion where you get to the top of the trajectory, work all that stuff out, and then work out the second part coming down and hitting the top of the building? And the answer is really that you don't, because the acceleration is going to be that 9.8 meters per second squared through the entire motion. So there isn't any need to sort of be thinking about something different happening here at that top of the trajectory. So in fact, it's really going to be pretty straightforward. We know the time, and we know the initial velocity in the y direction. So we can just use this equation for y as a function of time and plug in the time that we know. So I'll slide that equation down over there, and then put in the various values that we've calculated. The 36.4 is the meters per second, is the initial speed. Put in the time, put in the acceleration due to gravity, And bingo, 52.0 meters is the height of the building. So that's H. That's the answer to the first part of the problem. So that was pretty straightforward. The next piece says, find the speed of the stone just before impact. So again, just a fraction of a second before impact. It's clear its velocity vector is going to be oriented that direction. We know that it has a horizontal component and a vertical component. And don't forget, the horizontal component is just that constant 21 meters per second. The x component of the velocity doesn't change. Sometimes that's hard to sort of not to believe that. It feels like there should be something else going on there, but it's just a constant v0x. We are, of course, ignoring air resistance. Otherwise, that would have an impact, but all of these problems here in this chapter are ignoring air resistance. So we know the x component of the velocity. Now we also need to know the y component of the velocity down here, but it's clear we just need to use the constant acceleration equation in the y direction and figure out what that component is. So again, I'll slide that equation down over here. We'll plug in the various numbers. And when you work that out, it comes out to be minus 17.5 meters per second. And minus is what we expected because it's oriented now downward, so it's in the negative y direction. So now we've got the x component and the y component of the velocity right at that particular point. So we can do the standard thing, the Pythagorean theorem, to find out what the magnitude of that speed is. And that we just have to put in the x and y components and square them. Notice, of course, don't make any mistake here, the minus sign doesn't really matter because we're squaring it, so that minus sign is going to disappear. We add those two numbers together, then take the square root, and that comes out to be 27.3 meters per second. Now, we could calculate an angle here, but the problem only asks to find the speed. So notice they're giving us a little bit of a break. We don't have to actually worry about the direction of this velocity. All right, that takes us really to the last part then. That says find the maximum height reached above the ground. So again, this is really pretty straightforward. You want to constantly remind yourself that the x and the y stuff is completely separate. So even though the trajectory is this thing going up and over here, as far as we're concerned, the y component is all we're worried about, and we just go directly up, we turn around, and we come back down. So you can completely ignore the fact that there's stuff going on in the x direction and just think y components here entirely. And then how do we find out how high that goes? Well, we could calculate time or do various things, but I think the most straightforward thing to do is, let me reserve a little space over here on the right-hand side for this solution. The most straightforward thing is to just use that third equation that says final velocity squared is the initial velocity squared plus 2 times a times the change in distance. And here, notice again, it's a minus sign that comes in because the acceleration is in the negative direction. The y final minus y0 is, of course, just the height h. So that goes in there. And then remember that the vertical component is going on here. And at the top of the trajectory, the y component of the velocity is 0. So in fact, this guy is going to be 0. Now, it can seem a little confusing because, of course, the x component of the velocity here isn't 0. The velocity is equal to that 21 meters per second in the x direction because it's always got that component in the x direction. But that's why I'm thinking strictly y direction, as in sort of thinking about in the axis, this guy is going to be 0. So we can plug in those numbers, 0 on the left-hand side, the v0, and then minus 2ag times h. So now it's really just a matter of solving for h. That's not too hard to do. And then plugging in numbers. We've got that y component of the velocity, and 2 times the 9.8 meters per second squared. Let's just stop for a minute to notice meters per second squared gives us meters squared per second squared. We divide out meters per second squared, so we're left with units of h, and that comes out to be, when you plug it into your calculator, 67.6 meters. So that's then the answer to C, and we're all done.